this video, we're going to introduce the polar coordinate system, which is a way of representing locations in the plane using trigonometry. So our normal coordinate system we use is what we call the Cartesian coordinate system. So every location within the plane is represented with an x and y coordinate. So the x coordinate tells us how far we travel from the origin horizontally to get to our point's location, and then the y coordinate tells us how much we travel vertically. So the Cartesian coordinate system is what we call a rectangular system. In other words, every time we travel an x coordinate and a y coordinate in order to get to a particular location, essentially we're drawing the length and the width of a rectangle. So if you were to draw the x distance, draw the y distance that it takes to get from the origin to whatever point we're looking at, you could essentially draw a rectangle from that, hence a rectangular coordinate system. A coordinate system we can really just think of as a grid though. We're taking the plane and we're essentially just laying a particular grid on top of that plane, and the grid allows us to represent specific locations. There are other types of grids other than the horizontal and vertical line grid that we're used to that we could lay on top of the plane and thereby represent locations. So one of them is what we call a polar grid, hence the term polar coordinates. So a polar coordinate system is not going to define locations in terms of horizontal and vertical displacement. It's going to define a location using distance, so actual diagonal distance from the center of the plane, and direction, which we can also think of as rotation. So when we look at the polar coordinate system, the grid that we lay over top of the plane, it consists of a fixed point in the center, which we call the pole. So in the Cartesian coordinate system, we call this the origin. In the polar coordinate system, we call this the pole. From the pole, we have a ray emanating out, which we call the polar axis. So the polar axis is going to lay on top of what we normally think of as the positive x-axis. Now each point in the plane is defined as an ordered pair, but it's not going to be x comma y, it's actually going to be r comma theta. So r is the directed distance from the pole to get to our point. So it's the amount of distance we would have to travel in a particular direction to get to the point from the center of the coordinate plane. Now theta is going to tell us how far we would have to rotate around starting from the polar axis to get to our particular location. So r tells us, well, how far do we have to go out in terms of distance in order to get to our location. Theta tells us if we travel that distance, well, how far would we have to rotate around from the polar x-axis, or again, what we can kind of think of as the positive x-axis, in order to get to our location. So let's draw a picture of what this is going to look like. So in general, this is going to be the grid that we use to represent polar coordinates. You'll notice it looks a lot like the unit circle. If we were to just look at the first circle in here, that essentially would represent the unit circle. But notice it's not just a circle of radius 1. We have a circle of radius 2, a circle of radius 3, and then so on and so forth. So each of these rings that we have on our grid represents the possible values for r. So if r had a value of 1, that tells us our point lies somewhere on that first circle within the grid. If r were 2, then our point lies on the second circle, and then so on and so forth. And theta tells us, well, once we picked the circle that we're going to be on, how far would we have to rotate from the polar axis in order to get to our point, wherever our point happens to be. And so that's going to tell us where our particular point is located. So let's label a few things. So again, this is going to be the pole. What we think of as the origin normally we call the pole. The positive x-axis we now call the polar axis. We think of that as the starting point for any rotation. And then suppose we choose a particular point, and suppose this is going to be the point that we want to represent the location for. R is going to be the distance that it would take to get from the pole directly to that point. So that's going to be R. Think of r like radius. And then theta is going to be the amount of rotation we would have to take in order to get from the polar axis to our particular point along the particular grid circle that we want to travel along. Now, one thing that is unique about polar coordinates versus rectangular coordinates is rectangular coordinates describe a location uniquely. In other words, if we pick a location in the plane, only one pair of x and y coordinates describe that location. And also, if we were to write rectangular coordinates, write a particular x and a particular y, that only describes one location in the coordinate plane. So every point in the coordinate plane is matched uniquely with one x-y pair. That is not necessarily the case with polar coordinates. So when we're talking about the polar coordinate system, there are actually many different ways to describe a particular location using two different things. Number one, using additive inverses for r. In other words, r versus negative r. What does r mean? Well, if we say we have a particular value of r, that tells us along the polar axis, travel out to that particular ring. Negative r means we travel out to that ring in the negative direction, which would then match with a different amount of rotation in order to get to our particular point. So if we have a particular value of r, well, the negative version of that value could also be used to map to a particular location in the polar plane. And then also we can use coterminal angles for theta. So for instance, the point I've drawn right here, it looks like it's probably at 60 degrees based on the values we typically assign for those particular locations. And so it looks like we're at maybe 1, 2, 3, 4, so r would be 4, and then 60 degrees. Well, we know that we could represent this amount of rotation, or we could represent this location using this amount of rotation plus additional full rotations, or minus additional full rotations. So every angle that happens to be coterminal with 60 degrees also represents an amount of rotation that would take us from the polar axis to the particular point we want to represent. And again, we could also start in the negative direction with a negative r, and there would also be amounts of rotation that could take us back to this particular location. So there's never going to be just a single way to represent a location using polar coordinates. There are always going to be infinitely many ways to represent polar coordinates. Now, typically, we want to focus on choosing whatever angle would represent our location that happens to be between 0 and 2 pi. So starting from 0, starting from the polar axis, and choosing the shortest angle, the shortest positive amount of rotation that would take us to our particular location. Now, one thing we're going to talk about also is how we convert between coordinate systems, and that's what we're going to focus on in this particular video. So this is where the trigonometry comes in. So we're going to use trigonometric relationships to express our rectangular coordinates, x and y, in terms of polar coordinates, and vice versa. So essentially we have conversions. So if we have a point in polar coordinates, in other words, we have r and theta, and we want to convert to rectangular coordinates, x and y. Those particular rectangular coordinates are defined in terms of r and theta in the following way. So x is always going to be r times the cosine of theta, and y is always going to be r times the sine of theta. Now, where does this come from? Well, let's imagine that we also were to use x and y coordinates to represent this particular location. And we've done this a number of times. Every time we look at an angle in the unit circle, remember, we can always draw a vertical line from our particular terminal point to the x-axis, and that gives us a right triangle. And so this would then be labeled as x, and this would be labeled as y. So not only can we think of this as being theta, but we can also think of this angle right here as being theta. So notice with this particular diagram, we now have x and y, rectangular coordinates, and we also have r and theta, our polar coordinates that represent this particular location. So how are all of these values related? Well, they're related based upon our trigonometric relationships. So how could we represent the cosine of theta, for instance? Well, the cosine of theta we know is always going to be defined as the adjacent side over the hypotenuse. So adjacent is x, hypotenuse is r. So that's going to be x over r. And if we were to solve for x in terms of r and theta, we could multiply both sides by r, move it over, so we have x is equal to cosine, or r times cosine theta. So if we were given r and theta to represent this particular location in polar coordinates, that would be enough information for us to find the corresponding x coordinate that would map to that particular point. Now, same kind of thing for y. If we want to relate y, theta, and r, we can use the sine function. So the sine of theta is going to be the opposite side over the hypotenuse. So sine of theta is equal to the opposite side, which is y, divided by the hypotenuse, which is r. And if we wanted to solve for y in terms of r and theta, we have y is equal to r times the sine of theta. So again, if we are given r and theta representing this particular location, we can find a corresponding rectangular y coordinate by multiplying r times the sine of theta. So these are going to be the conversions we use when we want to go from polar coordinates, r and theta, and find the corresponding rectangular coordinates, x and y. Now what if we want to go in the other direction? In other words, suppose we're given x and y, rectangular coordinates, and we want to find the corresponding polar coordinates. We have similar relationships. One involves a trig function, and one involves a relationship that we've used a lot, specifically when we want to solve for the sides of a right triangle. So imagine for a moment that you were given x and y, and you want to find r and theta. In other words, r and theta, those are the things we don't know. All we know is x and y. Well, what relationships could we write that would allow us to take x and y and generate r? Well, we know because we're in a right triangle, x, y, and r have to be related in a specific way. Their relationship can be expressed by the Pythagorean theorem. So if we wanted to solve for r in terms of our given x and y, the Pythagorean theorem says that r squared is equal to x squared plus y squared. Now, why do I not solve for r in this case? I'm going to leave it like this. We also have to keep in mind, again, that r could be positive or it could be negative. If r is positive, it just means we're starting along the polar axis. If r is negative, it means we're starting along the negative polar axis. So in order to leave it open-ended and allow for both possibilities, we just express the relationship in that manner. Now, what if we also wanted to solve for theta in terms of x and y? Well, this is where the trigonometry is going to come into play. So if we have x and y in relation to theta, those are going to be the adjacent and the opposite sides. So the trigonometric ratio that relates the adjacent and the opposite could either be cotangent or what we're more familiar with, which is tangent. So the tangent of theta, given that theta is what we want to find, is going to be the opposite side divided by the adjacent side. So y divided by x. And so again, if we're given x and y, we know what this ratio will be. The tangent of our unknown angle, what we're trying to find, is going to be the ratio of y over x. Now we do have to keep in mind, in this kind of situation, if we were to find theta using specifically the inverse tangent, we know that's only going to take us to something that's in the first quadrant or in the fourth quadrant. But what happens if the point we're trying to represent is in the second or the third quadrant? Well, that's when we're going to go back to what we know about the unit circle, what it tells us about our trigonometric values, and how we find the values for tangent, the corresponding radian measures around the unit circle. But those four relationships, I'm going to box those in, those four relationships pretty much give us everything we need to know about polar coordinates versus rectangular coordinates, and how one is related to the other if we want to convert between coordinate systems. So let's look at a few examples. So for these next few examples, we want to do a few different things. Okay, so we've been given a point in polar coordinates. We've been given r and theta. R is always the first coordinate, theta is always the second coordinate. And the first thing we want to do is plot the point, plot it in the polar plane. We want to find two other polar representations of the point. So one where r is greater than 0, one where r is less than 0. And then we also want to convert the point to rectangular coordinates using those conversions. So it's a good idea anytime you want to do anything with a polar point, either finding other polar representations or converting it to rectangular coordinates, it's a good idea to graph it. So take a little polar coordinate grid and graph it. Now what I recommend for graphing here is graph using the angle first. In other words, identify where 5 pi over 6 would be if we started from the polar axis. So remember, think of this like the origin. We call this the pole. And the polar axis, think of that like your positive x-axis. That's where you normally start rotating. Think of that as 0 rotation, starting there. So we want to rotate to the angle 5 pi over 6. So from the polar axis, we rotate around, and 5 pi over 6 is going to take us over here into the second quadrant. Now we know the value for r is going to be 3, which means along that particular line, we want to go out to the third ring from the pole, from the center. So 1, 2, 3, third ring. So this is going to be the particular point that we're looking at. So that is the location. Notice that it's in the second quadrant. So already, thinking in terms of rectangular coordinates, we know that the x coordinate we find is going to have to be negative, and the y coordinate we find is going to have to be positive. Now let's focus on polar coordinates first though. So we want to find two other representations of this particular point, this particular location, one where r is greater than 0 and one where r is less than 0. So if r is greater than 0, that just tells us that we're starting along the positive polar axis. So in other words, we start rotating from this location and we go around to here. The easiest way to find another angle that represents that location when we're choosing the same value for r is to just find a coterminal angle. So if r is greater than 0 and we already have an r value of 3, we know the additional r value we're going to have to use is 3. All that r tells us is which circle along the grid we end up rotating along. So this particular point is on the third ring. That means any other representation we have for it has to take us to the third ring. So either the third ring in terms of r is equal to 3, or the third ring in terms of r is equal to -3. So again, if we want to start right here, start along the positive polar axis, we could rotate to 5 pi over 6, and then we could get back to the same location if we added on another full rotation and found a coterminal angle. So one way to find another representation would be to take our value for theta and then add on an additional rotation. And keep in mind we could subtract a rotation as well. I'm just finding a positive angle instead of a negative angle in this case. So 5 pi over 6 plus 12 pi over 6, which would give us 17 pi over 6. So that would be another value for theta associated with r is equal to 3 that would take us to this particular location. So if we were going to graph using r equals 3 and 17 pi over 6, 17 pi over 6 means we've gone 12 pi over 6, 13, 14, 15, 16, 17 pi over 6. And again, we started along the third ring, so we end up on the third ring as well. So our coordinates would be 3 and then 17 pi over 6. Now, what if we wanted r to be negative? This is where having the graph is going to be handy. Now, again, this particular point is on the third ring, which means the only options for r are either going to be 3, or in this case, r is going to be negative 3. That's the only way we can end up on the third ring when we graph using polar coordinates. But what would an associated value for theta have to be if r is negative 3? Well, imagine if we started along r equals negative 3, which means, again, rather than going out along the positive polar axis, we're traveling 3 units along the negative polar axis, which takes us to the third ring, but starting over here. Well, imagine starting at that particular location and then rotating in the positive direction in order to get back to this particular location. So how far would we have to rotate? Well, if we were to rotate halfway around, that means we've traveled pi radians. Okay, so we're not at pi radians where we normally think of pi radians, but the amount of rotation we've made is pi radians. And then add on another pi over 6, 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 for a total of 5 pi over 6 additional radians traveled, which would be a total of 11 pi over 6 radians. So it's important to keep in mind what we normally think of as 11 pi over 6 is located right here, right? We're thinking about how much rotation we've made from where we started. So this would be pi radians around that amount of rotation, and then 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6 radians, right before we get back to our original point where we started. So just a little bit left to get from that to one full rotation again. So in that case, our coordinates would be negative 3 and 11 pi over 6. And that, of course, is if we want a positive value for theta. What if we wanted a negative value for theta? Well, if we were going to start at negative 3, notice we also could just rotate really quickly back in the negative direction. That would be negative pi over 6 radians. And that would also take us to the same location. So that would also give us another value for theta to represent this particular point. Okay, let's now convert this particular polar point to rectangular coordinates. In other words, this particular location is unique. This is its representation in polar coordinates. Well, how would we represent that location if we were talking about x and y coordinates? That's the question we want to answer. So our x coordinate is always going to be defined as r times the cosine of theta, and we talked about y a moment ago. So in this case, r is going to be 3, and then theta is 5 pi over 6. So we're taking the cosine of 5 pi over 6. And of course, we get that value from the unit circle. So that's going to be 3 times the cosine of 5 pi over 6. Well, the cosine of 5 pi over 6 is going to be negative root 3 over 2. And so if we combine those together, think of this as 3 over 1. So the 3 goes to the numerator. So that's going to be negative 3 root 3 over 2. That's going to be our x coordinate. Now what about our y coordinate? Y is always defined as r times the sine of theta. So that's going to be 3 times the sine of 5 pi over 6. Now we know the sine of 5 pi over 6 is going to be positive 1/2. So 3 times 1/2 is going to be 3/2. And as we expect, if we're in the second coordinate or second quadrant in terms of location, the x coordinate would be negative, the y coordinate would be positive. So our coordinates are going to be negative 3 root 3 over 2 and 3/2. And again, keep in mind, this particular ordered pair is unique. This is the only pair of x and y coordinates that represent this location, whereas we just demonstrated There's at least 3 ways to represent this point in polar coordinates, and of course there are many more if we were to just use coterminal angles from there. Okay, let's try another one. So again, same directions. We want to graph, we want to find 2 additional polar representations, and then convert to rectangular coordinates. So now we have a positive r value, but our value for theta is negative, which just means we're rotating clockwise rather than counterclockwise. Okay, so again, I like to start with the value for theta. So negative 2 pi over 3. That means we're starting along the polar axis and rotating negative 2 pi over 3 radians. So positive 2 pi over 3 radians would take us over here. We want to rotate the same amount but in the negative direction. So negative pi over 3 and then negative 2 pi over 3. And then since r is 5, that means along that particular line, or that particular ray technically, we go out to the 1st, 2nd, 3rd, 4th, 5th ring. So that's going to be the location represented in those coordinates. So now let's find 2 other ways to represent that particular point. So for r greater than 0, well, we know we're on the 5th ring, which means r has to be positive 5. When r is less than 0, that means r is going to be equal to negative 5. Only r values of 5 and negative 5 can take us to the 5th ring. Okay, so for r greater than 0, again, another option is to just take our angle and find a coterminal angle to it, and that would allow us to go to the same location. So I'm going to take my angle, negative 2 pi over 3, and I'm going to add on a rotation, full rotation. So that's going to be negative 2 pi over 3 plus 6 pi over 3. And so when I add those two together, that's going to be positive 4 pi over 3. So another pair of coordinates for this particular location are going to be 5 and 4 pi over 3. So let's verify that this does in fact represent the same location. So 4 pi over 3, starting from the polar axis, pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. Okay, so that takes us to what looks like probably a similar location. And then if r is 5, again, that tells us we go out to the 1st, 2nd, 3rd, 4th, 5th ring. So that does in fact take us to the same location. Now, what if r is less than 0, which means, again, rather than starting along the positive polar axis, we're starting along the negative polar axis and we're rotating from there. So imagine starting out on the 5th ring in the negative direction. Well, how far would we have to rotate in the positive direction to get to this particular point? Well, if we're starting right here, all we have to do is rotate pi over 3 radians, that particular amount of rotation, in the positive direction. So a representation for this point with a negative value for r is going to be negative 5 pi over 3. And now let's find our rectangular coordinates. Now, because this point is in the 3rd quadrant, we know the x should be negative and the y should be negative as well. So x is going to be r times the cosine of theta, so our r is 5, times the cosine of negative 2 pi over 3. So what is the cosine of negative 2 pi over 3? Well, if we were to think of this like the unit circle, we know negative 2 pi over 3 is down here. It's coterminal with 4 pi over 3, which means we can use the values that we know for 4 pi over 3 to find this particular value. So at 4 pi over 3 radians, the cosine has a value of negative 1/2, which gives us an x-coordinate of negative 5/2. What about our y-coordinate? So y is going to be r times the sine of our angle. And again, rather than thinking of it as negative 2 pi over 3, a coterminal angle to that is 4 pi over 3. So we know those two angles, those two radian measures, have all the same trigonometric values, and the sine at 4 pi over 3 is going to be negative root 3 over 2. And so we combine all of that together, and our y-coordinate is going to be negative 5 root 3 over 2. So our rectangular coordinates are going to be negative 5 halves, negative 5 root 3 over 2. And again, they're both negative, just like we expect, based upon the location we ended up at. Okay, let's try another couple of examples. So notice in both of these cases, our value for r was positive. What happens if we start with a value for r that's negative? Well, the answer is nothing really changes. We have essentially the same procedure. We just have to be a little bit more careful when we graph. So negative 3 pi over 4. Okay, so again, we're going to start with theta in order to graph. So where does 3 pi over 4 take us? Well, starting from the positive polar axis, and you might be thinking, well, why am I doing that? I'm at negative 3, right? I'll show you why in just a moment. So starting from the positive polar axis, we're traveling pi over 4, 2 pi over 4, 3 pi over 4 radians in terms of rotation. Now, negative 3 tells us that we're traveling to the third ring, but from this particular location, we're traveling to the third ring in the opposite direction, the directly opposite direction. So if this is 3 pi over 4 radians from the positive polar axis, negative r would take us along this particular ray, the ray that is opposite the one generated by our rotation. So negative 1, negative 2, negative 3. Now, if we were to start with r and then graph theta, that means we would start negative 1, negative 2, negative 3 over here, and then rotate pi over 4, 2 pi over 4, 3 pi over 4 radians from there. So there are alternate ways to graph. You can graph from theta or from r first. You just have to make sure you know what these negatives mean. What does a negative r value mean? What does a negative value for theta mean? Okay, so let's find some additional polar representations. So r is greater than 0. Well, our original r is less than 0. So if r is greater than 0 and we know we want to be on the third ring, we know the only other value for r we could have is r is equal to 3, which would mean starting right here and then rotating from there. So if we were to rotate from this particular location along the positive polar axis, how far would we have to rotate in order to get to this particular point? Well, we would have to rotate all the way around down into the fourth quadrant, which would be a total of 7 pi over 4 radians. So a polar representation where r is greater than 0 would be 3 and 7 pi over 4. Now, if r is less than 0, that means we're using the same value for r. And this is where those coterminal angles are going to come into play. So keep in mind, this particular point took us to this location based on this value of r. So if we were to just find a coterminal angle to 3 pi over 4, it's going to generate the same location because we're assuming that we started with the same value for r. So 3 pi over 4, we're going to add on 2 pi radians. So that's going to be 3 pi over 4 plus 8 pi over 4, which is 11 pi over 4 radians. So another polar representation where r is negative would be negative 3, 11 pi over 4. Now let's verify that that does in fact make sense. So let's start with the rotation. So starting along the positive polar axis, if we were to make a full rotation all the way around, that's 8 pi over 4, 9 pi over 4, 10 pi over 4, 11 pi over 4. Now you may be thinking, well, we didn't end up where we're supposed to. But remember, r is negative, which means when we graph the actual point, we're going to travel along the ray in the opposite direction. So -1, -2, -3. And so it does take us to the location we want. So what about the rectangular coordinates? Well, since this particular location is in the 4th quadrant, x would be positive and y would be negative. So what are those values going to be in this case? So x is going to be our value for r, which is -3, times our cosine of 3 pi over 4. So -3 times the cosine of 3 pi over 4, which is -√2 over 2. Notice those two negatives multiplied together to give me a positive. So that's going to be 3√2 over 2. And of course we can put it all under 3. Okay, and then my y is going to be -3 times the sine of 3 pi over 4. 3 pi over 4, the sine is positive √2 over 2. So that's going to be -3 times positive √2 over 2. And here the negative is going to stay. So -3√2 over 2. And so our coordinate pair, +3√2 over 2, -3√2 over 2. Notice again, positive x coordinate, negative y coordinate, exactly like we expect. Okay, so let's look at the very last combination. So here we had a -r and a positive theta. What if both coordinates are negative? Well, again, we do it the same way as before, but we do have to be very careful as we graph. We have to make sure we know what -r means and what negative theta means as well. So let's start with our value for theta, so -pi/3, so starting along the polar axis, -pi/3, that would be pi/3 radians, but in the negative direction, so that would take us over here. And then -4 says that if we look at that particular ray, there at -pi/3, we want to travel along the ray that's directly opposite to that. So -1, -2, -3, -4. So that's going to be our location in this case. Okay, so let's find some additional polar representations. So what if r was greater than 0? Well, in order to end up on the 4th ring, r either has to be -4 or +4. So in this case, r would have to be +4. What would theta have to be in this case? So assuming we started along the positive polar axis, where r is +1, 2, 3, 4, how much would we rotate if we wanted to go in the positive direction in order to get to this location? Well, we could travel pi/3 units and then 2 pi/3 units, radians. So 2 pi/3 would also take us to the same location. Now, if r is negative, that means we're keeping the same value for r, and we could take a value for theta that's coterminal. So again, coterminal just means we end up right back where we started, and as long as the value of r is the same, then just using a coterminal angle will take us to the same location. And again, we can always verify that. So -pi/3 plus 2 pi, that's going to be -pi/3 plus 6 pi/3, which is 5 pi/3. So the other pair of coordinates, or rather another, not necessarily the other, but another pair of coordinates, would be -4 and 5 pi/3. So let's verify that that makes sense as well, that the graph's the same way. So 5 pi/3 means we're starting along the polar axis. We rotate around to where 5 pi/3 would be, which would be down here. And then -4 for r tells us that we're traveling not along that ray, but along the ray that's opposite it. So 1, 2, 3, 4. And so it takes us to the same location. And now let's look at our rectangular coordinates. So x is going to be -4 times the cosine of -pi/3. So what's that going to be? Well, what is the cosine of negative pi over 3? This is where those coterminal angles are going to be helpful. So negative pi over 3 is the same thing as positive 5 pi over 3. So what we know about 5 pi over 3 will be the same as what we know about negative pi over 3. So at that particular location, the cosine has a value of positive 1/2. So we multiply that, simplify it down. It's going to be negative 2. And then y is going to be negative 4 times the sine of negative pi over 3. And again, negative pi over 3 would take us right here. The sine at that location is negative root 3 over 2. Okay, so our two negatives combine to give us a positive. 4 and 2 reduce, so that's going to be positive 2 root 3. So our ordered pair is going to be negative 2 root 3. Now you may be thinking, okay, we had a point over here, so why am I looking at an angle down here? It doesn't seem to match the same location that we're interested in. Well, remember, in this case, r was negative. So the actual angle we're looking at, just by itself, independently, the angle we're looking at is an angle that rotates and takes us into the fourth quadrant, assuming that we start along the positive polar axis. So how do things end up being adjusted so that they take us where we want to be? Well, that's because we're multiplying by a negative value for r. So we're looking at an angle that takes us down into the fourth quadrant, but the fact that r is negative tells us we would travel in the directly opposite direction, which takes us into quadrant 2. So our x should be negative, our y should be positive, and sure enough, we end up with coordinates that have those particular signs. So that gives you an example of all the different situations you can see in terms of graphing. Different signs for r, different signs for theta, how we convert to rectangular coordinates, how we find other polar representations. So now let's talk about converting in the other direction. So what happens if we have rectangular coordinates, x and y, and we want polar coordinates? Well, again, converting in this case, finding polar coordinates means there are going to be multiple versions of how we could have polar coordinates, because there's never just one unique set of polar coordinates. So when we convert, typically we're going to start with just the positive value for r, and then we'll go from there in order to find a negative value for r. And again, graphing is going to be really helpful. So particularly when you want to find other polar representations, having a graph of your point is going to be very helpful. Now, I don't want to graph negative 3, 3, but it is helpful at least to know what quadrant that should be in. So negative 3 and then positive 3, that would take us into the second quadrant. So I am going to make a note of that. That is in quadrant 2. That means when we find polar representations, they should take us to a location that is within the second quadrant. So if we want a polar pair where r is greater than 0, we're finding r, we're finding theta, let's just start with our conversion equations. So the equation to find r is going to be r squared is equal to x squared plus y squared. So we can plug in our x and y. So that's going to be negative 3 squared plus positive 3 squared. Well, negative 3 squared is 9, and then 3 squared is 9 as well. So that's going to be 18, which means that r is going to be the positive or negative square root of 18. Now we know square root of 18, 18 is not a perfect square, but it is divisible by the perfect square 9. So we can take the square root of 9 separately, which would give us a 3, and then we would be left with the 2 from that 18. So that means in order to represent this location in polar coordinates, either we have to have a positive 3 root 2, or we have to have a negative 3 root 2. Okay, so if we want r to be greater than 0, we know we're going to use positive 3 root 2. which means from a graphing point of view, we're starting along the positive polar axis, and then we're rotating from there. Now, what about our value for theta? So we would need an angle that takes us from the positive polar axis into the second quadrant. So our relationship for theta, we know that the tangent of theta is equal to our y-coordinate divided by our x-coordinate. Well, in this case, our y-coordinate is 3. Our x-coordinate is -3, which reduces to -1. So the tangent of our angle, whatever that angle happens to be, is going to be -1. Now, there are different locations within the unit circle where we end up with a tangent of -1. But we want the angle that's represented by the second quadrant. So where in the second quadrant, rotating from 0, do we get an angle that has a tangent of -1? Well, the only angle in the second quadrant that has a tangent of -1 is going to be the angle 3 pi over 4. So that is going to be our value for theta. So let's graph that. So 3 root 2, okay? So it's going to be, that number is just a little bit bigger than 4. It's between 4 and 5. So 1, 2, 3, 4, and then just a little bit bigger. And then 3 pi over 4 would take us right there. Excuse me. Somewhere like that. Okay. Now, what if r is less than 0? Well, we don't need to go through this whole procedure again. We know that r is either going to be positive 3 root 2 or negative 3 root 2 in order to take us to the correct ring, which happens to be a ring between the 4th and 5th rings. So that means r is going to have to be negative 3 root 2, which means we're starting at that location in the negative direction. So how far would we have to rotate in order to get back to this location if we started over here? Well, if we take a halfway rotation, that's going to be pi radians, and then that would be an additional pi over 4, so 5 pi over 4, and then 6 pi over 4, and then 7 pi over 4. So if we were to allow r to be negative 3 root 2, then theta would have to be 7 pi over 4, assuming we want the smallest positive rotation. So another pair would be negative 3 root 2 and 7 pi over 4. Okay, let's try another one. So 7 and negative 7 root 3. Well, first off, where would that point be located? So x is positive, y is negative, x is positive, y is negative. That means this would be something in the 4th quadrant. So when we find our polar representations, they need to graph as points in the 4th quadrant. So what if r is greater than 0? What would r have to be in order to take us to this location where it's greater than 0? So we know r squared is equal to each of our coordinates squared, so 7 squared plus negative 7 root 3 squared. And I didn't pull up the calculator for this video, so you may have to do that out to the side. So 7 squared is going to be 49. Let me pull up mine as well. Now, when we're squaring the next term, you're going to have to be careful. You have to square both the 7 and the root 3. So we square the 7 and we get 49. If we square root 3, we get a 3. And then, of course, the negative squares and becomes positive. So if you were to multiply 49, which is 7 squared, times 3, which is root 3 squared, you are going to get 147. And so if we add those two together, 147 plus 49 is going to be 196. So that means r is going to be the positive or negative square root of 196. And as it turns out, 196 is actually a perfect square. So that's either going to be positive or negative 14. So if we want r to be greater than 0, of course, we're going to have to choose positive 14. Now, for purposes of graphing this one, notice we only have 5 rings. So I'm just going to choose the outer ring, and I'm just going to label it as a 14 in order to be able to graph, which is something we do with X and Y coordinates quite frequently. We can change the scale just in order to make our higher coordinates graph on a smaller coordinate plane. So I'm going to graph using 14 at the very end. Now, what about our theta? We need an angle that's going to take us from the positive polar axis all the way around to something in the 4th quadrant. Okay, so we know the tangent of our angle is going to be y over x, so -7√3, divided by our x coordinate, which is +7. So our 7's are going to cancel, leaving us with just a negative, so -√3. Now, how do we determine what value of theta gives us that value for the tangent when we're in that quadrant? Well, think of this, maybe more helpfully, as -√3/2 and then 1/2. So in other words, we have a value for sine that's √3/2, or in this case, -√3/2, and a value for cosine that's 1/2. So what value for theta would give us this value for sine and this value for our cosine? Well, that would have to be this particular angle, which is going to be 5 pi over 3. So theta, in this case, is going to be 5 pi over 3. So again, just to recap that, the sine, the y coordinate, -√3/2, cosine, the x coordinate, is 1/2, and so that angle down in the 4th quadrant would be the angle 5 pi over 3. So our coordinates are going to be 14 and 5 pi over 3. So if this is our 14th ring, then from there we rotate around 5 pi over 3 radians, which would take us to this particular location. Now, what if we wanted r to be negative? Well, we know in order to take us to the correct ring, it would have to be -14 rather than negative anything else. What about our theta? Well, -14 means we'd start on the same ring, but on the negative side of the polar axis. How far would we have to rotate from there? So this would be pi over 3 radians, and that would be 2 pi over 3 radians. So theta is going to be 2 pi over 3. So our other polar pair would be -14 and 2 pi over 3. Okay, so now we've converted in both directions. We've done both conversions with ordered pairs. So we know how to graph polar points, we know how to find multiple polar representations, and we know how to convert between polar and rectangular representations as well. So let's switch gears just a little bit. We have to keep in mind that as we graph ordered pairs can be combined together in groups to represent relationships among x and y, among inputs and outputs. In other words, things that can be represented also as equations. So the same conversions can be used to rewrite equations in different forms. So every equation that's in terms of x and y can also be written as an equation in terms of r and theta, and vice versa. So polar coordinates in general describe distance and direction, which we've already talked about. And again, direction, we can think of that as rotation, how far we're rotating from our polar axis to get to our particular location. So the fact that we're talking about rotation when we talk about polar coordinates means that polar coordinates are often beneficial when we want to write the equations of circles, ellipses, which is just kind of an egg-shaped graph, and graphs with loops. In other words, anything you could graph that involves some sort of rotation. In a lot of cases, the equations you'd write with x and y coordinates are very complicated, whereas the equations you can write in polar coordinates, they tend to be a lot simpler, just because polar coordinates already have this rotational component just naturally a part of them. So what we want to talk about now is how we would do the conversions, either from rectangular to polar coordinates or from polar coordinates to rectangular coordinates. So it's going to be important that we remember those conversions. Remember, we have 4 options for conversions. So we know x is always going to be equal to r times the cosine of theta. Y is going to be equal to r times the sine of theta. R squared is going to be equal to x squared plus y squared. And then the tangent of theta is going to be equal to y over x. So as we convert, it's going to be helpful to have that little list handy. Those are our options. Those are really our only options. Now, doing the conversion from rectangular to polar coordinates is usually a little bit more straightforward, because literally all we have to do is take every x and plug in an r and a cosine theta, take every y, plug in an r and a sine theta. When in doubt of any other options, we can always do that. Now, there may be some additional things we can do before making those substitutions that make our lives a little bit easier, but that's always going to be an option, just to directly substitute for x and y. Doing the conversions in the opposite direction may be a little bit more complicated, because we may be required to manipulate the equation just a little bit before we make those substitutions. Okay, so this particular equation, what would this look like if we graphed it? Well, we have our variables x and y, they each have an exponent of 1, so this would be a linear equation. It would graph as a diagonal line. So what would this look like in polar coordinates? What does the equation of a diagonal line look like in polar coordinates? Well, we don't have anything special we can do here except to just substitute for x and y. So in place of x, I'm going to put r cosine theta. In place of y, I'm going to put r sine theta. And that, for all intents and purposes, will convert coordinates. But as with rectangular coordinates, typically there's sort of a preferred form for how we want our equations to look. When we're talking about polar coordinates, the preferred form is to have r by itself. So just like we typically prefer to have y by itself when we're talking rectangular coordinates, when possible, if we're talking about polar coordinates, we want to isolate r. So notice in this case, of course, the parentheses don't really matter right now. It's just 2 times r times cosine theta plus r times the sine of theta is equal to 4. At this moment, I have 2 r's. Both of these terms have an r, but that also means that r could be considered a common factor. If I factor it out, then I can take 2 r's and make it look like 1 r. And so that's going to give me 2 times the cosine of theta plus the sine of theta, and that's going to be equal to 4. The benefit of doing that is now r can be isolated by just dividing out this factor. So I'm going to get r is equal to 4 divided by 2 times the cosine of theta plus the sine of theta. So that is going to be my equation in polar coordinates once we isolate r. And notice, arguably, this is more complicated than the original equation. Well, if the original equation graphs as a line doesn't really involve any rotation. So putting this equation in polar coordinates, the polar coordinates are potentially a little bit more complicated, just because what they're naturally used for isn't really something that comes up in an equation that graphs this way. Let's look at the next one. So x squared plus y squared is equal to 4. What is this going to graph as? Well, as it turns out, this is actually the equation of a circle centered at the origin. And specifically, it's going to be a circle with a radius of the square root of 4, which is 2. So that gives you a sense of what this looks like. And automatically, since we're talking about a circle is drawn with rotation. So we're going to find that polar coordinates are actually going to take this equation, which is fairly simple, and they're actually going to make it even simpler. So I want to show you two different ways you could simplify this particular equation, convert it to polar coordinates. We could do exactly what we did here. That's option 1. So let me make a note. Option 1. We can directly substitute for x and y. That is an option. So that would be r cosine theta squared plus r sine theta squared is equal to 4. So I need to square each of those factors in both sets of parentheses. So that's going to be r squared cosine squared theta plus r squared sine squared theta is equal to 4. Now again, the goal is to isolate r. So just like the previous example, I notice that I have an r squared in common, so I'm going to factor it out. And something else is going to happen as a result of that in this situation. So I'm left with a cosine squared plus a sine squared of theta, which is equal to 4. Now technically I could divide this factor out, but as it turns out I don't actually have to. This may look familiar to you. Anytime we take cosine squared and add sine squared, remember that Pythagorean identity tells us that this is identical to 1. So this is just 1 times r squared, which just leaves us with r squared is equal to 4. And if we take the square root of both sides, we're going to get r is equal to the square root of 4, which is 2. Now again, you may be thinking, we need a plus minus, right? When we take a square root in an equation, we put a plus minus. And normally, yes, we do. The reason we don't need plus or minus here is because of what this equation is telling us. This equation is telling us graph all polar points with an r value of 2, regardless of what theta is. So if you were to imagine, let me find a grid, there's a grid. If you were to imagine taking a grid like this, here's r equals 2. We're saying r has to be 2 and theta could be anything we want, which means starting from this location, we're just rotating. Theta can be whatever we want as long as we keep r to a value of 2. So we continue rotating, and notice we trace the whole circle just from a value of r is equal to positive 2. So essentially having the positive negative here makes something kind of redundant. Having just r equals positive 2 is going to give us all the ordered pairs that would graph that entire equation, graph that entire circle. So we don't actually need the negative 2 in this case. Now alternatively, we could also say that r is equal to negative 2, and that would be another appropriate representation of this equation. It just means as we graph, we would start from negative 2 and then just rotate that way. But again, we would be able to trace the entire circle regardless of which value for r we chose. So that is going to be our equation there. And notice, quite a bit simpler than the equation we started with. So that's option 1 if we just do a direct substitution. Now there's also a second option for how we could simplify this one. And let's go back to our list of conversions. X squared plus y squared. So we just directly subbed for x and y. But notice there's also an expression that already can be substituted for x squared plus y squared as a whole. We also can say that that's just identical to r squared. So we also could just directly sub in r squared for the entire left-hand side of the equation, which essentially takes us to this point in the problem, and we skip the first 2 steps. And then again, we take the square root of both sides, and we get r is equal to 2. So same answer either way. In this case, our equation was in a form where we were able to take a little bit of a shortcut. Okay, let's try another one. So x squared is equal to 3y. What would this look like if we graph this? Well, anytime we see a variable and then one variable is squared, the other one is to the first power, this is a parabola. This equation is quadratic, which means it would graph as a parabola. Now we don't have an x squared and a y squared, we just have an x squared and then a y that's linear. So that means probably the best option here is just going to be to directly sub for x and y. So x is r cosine theta, so we have r cosine theta squared, is equal to 3 times y, which is r sine theta. Okay, so square both factors. So that's going to be r squared cosine squared theta is equal to 3 times r times sine theta. Now, here's what you can't do that's very tempting to do. You may notice, okay, I've got r's on both sides, I'm going to divide it out. You can never divide out a variable and eliminate it. As soon as you divide out a variable in an equation and eliminate it, you also eliminate solutions to the equation, which means from the standpoint of graphing, you may eliminate some of the structure of the graph. So that's not allowed. As soon as you see anything with an exponent and then an additional instance of the variable that maybe has an exponent of 1, immediately everything needs to go to one side of the equation so that you can set it up for factoring. So I need to subtract this entire term and move it over. So that's going to be r squared cosine squared theta minus 3 times r times sine theta, and that's equal to 0. Okay, we now have a common factor of r. That's the only thing that's common between these two terms. So I'm going to factor that out. So I factor out that r, which leaves me with a single r here, and then a cosine squared. So r times cosine squared theta. We only had one r here, so we factor it out, and we're just left with negative 3 sine theta. And all of that is equal to 0. So now we can split things up. Now, if we just set r equal to 0, that just represents the pole. And we'll find that the pole is also represented as an ordered pair on the graph of everything that's left. So we don't actually need to keep this equation. Everything we need is going to come from this second equation we get when we set the remaining factor, the larger factor, equal to 0. Okay. And you'll notice here we only have one instance of r, which means it can now be isolated. So now I'm going to add this term, move it back over. So that's going to give me r cosine squared theta is equal to 3 times the sine of theta. And then I can divide that cosine squared. And so r is equal to 3 sine theta divided by cosine squared theta. Now this can technically be simplified a little further as well, since we know we have reciprocal and quotient identities. Anytime I see a trig function in a denominator or a ratio of trig functions, that's a red flag that maybe we could use one of those reciprocal or quotient identities. So let's pull out the 3 and notice what we're left with. We have a sine in the numerator and then 2 cosines in the denominator. So if I were to take one of those cosines and take its ratio with sine, sine over that single cosine would give me a tangent. Now what would I be left with? That takes care of the 3 and the sine. I'd be left with 1 cosine. So 1 in the numerator divided by cosine in the denominator would leave me with a secant theta. So that's going to be our simpler version there. So it's probably not obvious looking at this, but that actually is a parabola. That's the equation of a parabola. And a parabola does involve a little bit of rotation, not the same way that a circle does, but this is going to be the equation we would use to represent that in polar coordinates. Let's look at our last equation. So what is this an equation of? Well, believe it or not, this is also the equation of a circle. It's not a circle centered at the origin though. So as soon as we add or subtract onto our x and y coordinates, that represents a shift. So a horizontal shift and a vertical shift. So essentially we've changed where the center of the graph would be. The radius is still going to be the square root of this number over here. So this is still going to be a circle with a new center that has a radius of 5 in this case. So I'll just make a note that this is a circle, not centered at the origin. So what would its equation look like? Well, what can we do here? We could FOIL this out if we want. We can FOIL this out if we want. The drawback to doing something like that, though, is then we're going to have to make multiple substitutions for x and y. So I might just go ahead and make the substitution and then just go for there and see what happens from that point of view. So in place of x, we're going to sub our r cosine theta. In place of y, r sine theta. So r cosine theta plus 3 squared plus r sine theta minus 4 squared is equal to 25. So now we just need to FOIL this out. So our first term squared, keep in mind this does not mean square each term, it means FOIL it. So what we're really doing is r cosine theta plus 3 times r cosine theta plus 3. So if you need, pause the video and FOIL these out by hand. I'm going to show you how you get to the final answer for FOILing, but again, if you need, pause the video, do it by hand, take the moment to do that. That's going to be helpful. So our first pair, which would be r squared cosine squared theta, r squared cosine squared theta. Our outer and inner would both be 3r cosine theta, so we would have 6 in total, 6r cosine theta. And then 3 squared is going to be 9. And then we do the same thing over here, paying attention to the fact that we have a negative. So we square our first term, so r squared sine squared theta. Outer would be negative 4r sine theta. Inner would be negative 4r sine theta as well. They don't cancel, they combine to negative 8r sine theta. And then negative 4 times negative 4 is going to be positive 16. And then all of that is equal to 25. Okay. Notice the constants. If we have a 9 and a 16 over here, if we were to move them over to the other side and subtract, 9 and 16 adds to 25, and we have a 25 on the other side as well. So all of those end up canceling one another out if we combine all our constants. And again, that would be what happens if we move these two terms over. Now, what else happens? Well, looking at this, I see those squared terms, and those make me think of what happened right here when we did the conversion for this particular circle centered at the origin. Remember, those two terms grouped together and then the r squared factored out gave me something that canceled out and just reduced to 1. So I'm going to rearrange things a little bit in order to be able to do that. So I'm going to focus on these two terms. These two terms are added together. I can add things in any order I want. And if I were to just look at those two, they have that common factor of r squared. So I'm going to factor it out, which leaves me with the cosine squared theta plus sine squared theta, which we know is going to reduce to 1. We also have the 6r cosine theta minus 8r sine theta. So plus 6r cosine theta minus 8r sine theta. Now what about the other side? Well, remember, all the constants canceled one another out, and so we're just left with 0 on the other side. And all of this, we know that just reduces to 1. So what does that leave us with if this reduces to 1? Well, we have r squared, 6r cosine theta, 8r sine theta. Think back to kind of what we did here. Notice we had a common factor of r, and the goal is to isolate r, so factoring out r gives us the option to isolate it. We have an r in common among these three terms, so I'm going to factor it out. So if I factor it from the first term, which is now just an r squared, factor it out, we're left with a single r, so r. Here we're left with a 6 and a cosine theta, So plus 6 cosine theta minus 8 times sine theta. And then all of that is equal to 0. Now we're basically where we were before. We can split it up. Each of those factors set equal to 0. So if we split r equal to 0, again, that just represents the pole, which we'll find is represented by the rest of the equation as well. So we can essentially throw that away. We don't really need it. So the other one, r plus 6 cosine theta minus 8 sine theta is equal to 0. And notice here there's not going to be any division necessary. R is its own term, and the other two terms in the problem don't have an R. So I can just move these two terms over to the other side, and R will be isolated. So if I add 8 sine theta and subtract 6 cosine theta, I'm going to have R is equal to positive 8 sine theta minus 6 cosine theta. And that is going to be our equation. So again, believe it or not, that represents a circle. A circle not centered at the origin that happens to have a radius of 5. So you'll notice there's a good variety in terms of what conversion can look like. Keep in mind the actual conversions are pretty much the same every time, and when in doubt, you can always just directly sub for x and y. What varies from there is the algebra that it's going to take to put your equation in a more usable form, specifically to isolate r. So things like factoring, distribution, those kinds of things, those are the kind of strategies that we expect to see used. And we also end up using some of our trig identities to simplify things down or write them in a more convenient form. So now let's look at conversions in the opposite direction, which tend to be a little bit more challenging just because we don't always have a direct substitution to use. So some general strategies. Of course, we can apply one or more of the conversion relationships, and I'm going to write those down again. So we have x is equal to r cosine theta. And one note I do want to make about something like this, or something like y is equal to r sine theta. If we want to rewrite x and y in terms of r and theta, of course we can make those direct substitutions, but it can work the other way as well. So if we see an r times a cosine theta or an r times a sine theta, that can also be directly replaced with an x or a y. So every conversion factor can be used in both directions, just depending on what the goal is and what we see present in our equation. So these are going to be two of our conversion factors. And the other two we're going to use a little bit more when we do this type of conversion. So r squared is going to be equal to x squared plus y squared. And then the tangent of theta is going to be equal to y over x. So keep in mind, those are our only conversions. In terms of converting, we have to use some combination of these four relationships. Okay. What we're going to find is how do we generate these kinds of things in order to be able to replace our x and y, our rectangular variables, with our polar variables r and theta. So sometimes one of the goals is going to be to generate from an r squared in order to be able to use this particular relationship. So there's two ways to take an r and generate an r squared. We could technically multiply both sides of the equation by r, which may seem like the less obvious strategy, but if it allows us to then take something with a cosine or a sine and then add the r to that, that's then going to give us something to sub for x and y. So we can multiply both sides by r, and that generates an r squared from a single r. Or alternatively, if you see an r by itself and you want to make it r squared, well, you could also square both sides of the equation, which is probably what would seem more obvious. Now, which one you do is just going to depend on the equation. It's going to depend on what's already there and what sort of things you may be able to do in terms of substitutions using those conversions. Okay, so let's look at several examples here, and let's convert from polar to rectangular coordinates. So we have r and theta, we want x and y. So we're going to convert, and then we also want to identify the type of graph we're looking at based on our conversion. So for our first equation, we have r is equal to 2, and our goal is to get x and y, replace that r with x and y. So here are our options. Now, we don't have any trig functions present, so that means these first two are not going to be a good option. We don't have a theta present, so this last one's not going to be an option either. So the conversion factor we're going to have to use is going to be this one in the middle. Now we have an r. In order to use this conversion factor, replace r with x squared plus y squared, we need an r squared. And again, we have two options for getting an r squared. We can multiply both sides by r, or we can square both sides of the equation. Now let's look at each of these possibilities. If we were to multiply both sides by r, what would happen? And I'm going to write out what that would look like. If we were to multiply both sides by r, we're going to take this r, and then of course it will become an r squared, which was the goal. But whatever we do to one side, we also have to do to the other side. So we'll have something that we can then replace r squared with. We can replace that with x squared plus y squared. But what do we do with the remaining r? There's nothing to replace that with. Well, you may be thinking we could take the square root over here, which I guess technically we could, but you're going to make a really, really complicated equation. And so multiplying through by r is going to be problematic. It gives us something that we then can replace with x squared and y squared, but it also generates another r that we then have to replace as well. So potentially a better option in this case is going to be to square both sides of the equation. The benefit of doing that is we'll get the r squared we want, but the constant will stay constant. We won't introduce a new variable to the equation. So we square both sides, and we get r squared is equal to 2 squared, which is going to be 4. And then we can just do our direct substitution. So x squared plus y squared is equal to 4. What is that? That is a circle centered at the origin. Circle centered at 0, 0 with a radius of 2. So if we generalize what happened in this conversion, what that essentially tells us is that anytime we have an equation of the form r is equal to a number, that's going to generate a circle for us. And notice the radius is the number that r was equal to. You can think of r as essentially being radius. Think of r as representing the term radius. So anything of the form r is equal to a number generates a circle centered at the origin, or if we're in polar coordinates, we call that the pole, that has this value as its radius. And the next video we're going to talk about graphing polar equations, and we'll use these kinds of generalizations in order to make graphing a little bit easier. So that's going to be our conversion there. Now what about the next one? Notice this one only has a theta, it doesn't have an r. So we don't have any trig functions, we don't have an r, so these two conversions are not going to help us. Again, we don't have an r, so we can't use the third conversion. We want the conversion that only involves theta, which is going to be our final conversion. Tangent of theta is equal to y over x. Now, in order to use this conversion, we need not only theta, but the tangent of theta. So I'm going to apply the tangent function to both sides in order to put this in a form that's usable. So I'm going to take the tangent of theta, which means I also need to take the tangent of pi over 3. So tangent of theta, we'll worry about what that is in a minute, what we do with that. Tangent of pi over 3 is just going to be a number. And remember, it's going to be the sine of pi over 3 divided by the cosine of pi over 3. So at pi over 3 radians, our sine, our y-coordinate, is root 3 over 2. And our cosine, our x-coordinate, is going to be 1/2. And all of that reduces to just the square root of 3. So we now have tangent of theta is equal to the square root of 3. Well, once I have the tangent of theta, I now can substitute that with y over x, and that'll put us in rectangular coordinates. So that then becomes y over x is equal to the square root of 3. And we know when we're in x and y coordinates, typically we like to isolate y when we can. And we can do that here if we just multiply and move x to the other side. And so we have y is equal to the square root of 3, which is just a constant, times x. Well, this is a linear equation, so this would be a diagonal line. Think of this as something of the form y equals mx plus b, which it is. So m in this case is square root of 3. Now we don't see a number added on at the end, so automatically that means b, our y-intercept for this line, would be 0. In other words, we pass through the origin. So this would be a line with a slope of the square root of 3, whatever that happens to be, that passes through the origin. So passing through 0, 0. If we were to graph, that's going to be what we get. So what that tells us more generally is that any time we have an equation of the form theta is equal to a number, and typically it's going to be a radian measure, that is going to generate a diagonal line that passes through the origin. Now what's going to change is the slope of the line. So the slope of this line was based on what we got when we applied the tangent. If we were to change pi over 3 to, say, pi over 4, when we take the tangent of that value, we'll get a different value here. That value became the slope of our line. So a different constant over here would also result in a different constant over here. In other words, a different slope. But we can generalize the type of equation, the type of graph that it generates just based on the form. Okay, let's try another one. R is equal to 4 times the cosecant of theta. Okay. What can we do here? Well, we don't have anything to directly substitute yet. What are our options? So we've got x is equal to r cosine theta, y is equal to r sine theta, r squared is equal to x squared plus y squared, tangent of theta is equal to y over x. Well, first off, our last option, tangent of theta is equal to y over x. We don't have anything even closely related to tangent. And the fact that there is an r already in this equation means we're going to have to use one of the conversions that already involves an r. Now, because we do have a theta as well, and not just exclusively an r, the third conversion probably isn't going to help us either. The first two are going to be our options here. So we have a conversion involving cosine, a conversion involving sine. Now, notice we have neither sine nor cosine here. We have a cosecant. But we also have an identity that can take cosecant and can relate it to one of those two functions, specifically to sine. So in order to put this in a form where we can apply a conversion, it's going to be a good idea to go ahead and write cosecant in terms of sine. So we could rewrite this as r is equal to 4 divided by the sine of theta. So we know cosecant is equal to 1 over sine. That means 4 becomes our numerator. Now, how does this benefit us? What conversion do we have relating r and sine? Well, we have y is equal to r times the sine of theta. How does that relate to what we have right now? Well, we have an r on the left-hand side, and then we have something that has a sine of theta in the denominator. If we were to multiply both sides by the sine of theta, that would get this out of the denominator. It would move it to the other side, and that would give us an r sine theta on the left-hand side, which we then could directly substitute for. So that's going to be our strategy in this case. So we converted cosecant into its reciprocal, 1 over sine, and now we're going to move that sine theta over, which is going to give us r times the sine of theta is equal to 4. And based on our conversion, r times the sine of theta is going to be the same thing as y. So we have y is equal to 4. Now what does this look like? Well, this is also a line, but it's a special kind of line. This is a horizontal line. Any line of the form y is equal to a constant is a horizontal line. And in this case, it passes through the y-intercept at 4. So a horizontal line, if we want to be more specific, passing through the ordered pair 0, 4. So this line would not have an x-intercept. It's a horizontal line. The x-axis is down here. This is a line above the x-axis parallel to it. So it has a y-intercept only. So anytime we see something of this form, it converts to a form like this, which is going to give us a horizontal line. Okay, let's try one more. So r is equal to -2 times the cosine of theta. So I'm thinking, looking at this, that maybe we're going to use this conversion factor, x is equal to r cosine theta, but we're going to have to see. Okay, so we have r on one side, cosine theta on the other side. Now it's tempting to say that this is basically the same thing that we have right here, but it's not. Notice in this case, we had a trig function that we then could convert using its reciprocal identity, and then we were able to move that sine theta over and do the direct substitution there. The difference here is we already have cosine, and so we cannot multiply and move it over. That's not going to do anything for us. So what we did here, this strategy we used here, is not going to apply for this equation. So we're not going to be able to use that direct substitution, x is equal to r cosine theta. Well, what are our other options? Well, we have additional options. We have r squared is equal to x squared plus y squared. We have tangent theta is equal to y over x. This is probably not going to help us just because we have an r, so we're going to have to use some combination of these three. Now, in order to substitute for the r, we know we're going to need an r squared. And again, we know we're not going to be able to move that cosine, so that r squared relationship is the one we're going to have to use. So what are we going to do? Do we need to square both sides to get the r squared, or should we multiply by r? Well, let's think about what would happen in each case. What if we just squared both sides, like we did with the first example, and it seemed to help? If we just square both sides, we'll have r squared is equal to all of this squared, which would be 4 times cosine squared theta. Okay, so we could sub for r squared, that would be x squared plus y squared is equal to 4 times the cosine squared of theta. So this is good, but what about this part? We don't have anything to directly substitute for cosine squared. So this is probably not going to be a good approach because it leaves us with something that then is more complicated than what we started with, and something again that we can't directly substitute for. So our other option, besides squaring both sides to get an r squared, is to multiply both sides by an r. And imagining what that does, you may see why that's helpful. So imagine multiplying both sides by r. So we end up with r squared, and then if we do the same thing on the other side, we have -2 times r times the cosine of theta. And now we're going to be able to use that substitution for r cosine theta. And again, that resulted from multiplying both sides by an r. That generates the form that we need in order to be able to substitute an x in place of that r cosine theta. So now we're going to do our substitutions. So this is going to be x squared plus y squared is equal to -2 times r cosine theta, which is x. Okay, now we need to get this in the form we want. Now this is not going to require isolating y. Isolating y requires that we take a square root, we have to put a plus minus in all of it. It's going to be a mess. What we want is more of, let's see, let me find it, more of this kind of form. This is what we think of as a standard form for a circle. Notice we have x grouped into a binomial that's squared, and y is also grouped into a binomial that's squared. and we have a constant on the other side. We essentially want to do the same kind of thing here. So first thing we want to do anytime we want to factor something, everything goes to one side of the equation. So I'm going to add this 2x, move it over. So that's going to be x squared plus 2x, so keep those x's together, plus y squared, and that's equal to 0. So my goal is now to take this pair and make it look something like that. Okay. The strategy I use to simplify or rewrite something in this form is what we call completing the square. So I'm going to group these two terms, the two terms involving x, and completing the square, I'm going to make a note over here, completing the square. Completing the square is essentially a strategy we use in order to generate a trinomial that can be factored. So what we do when we complete the square is we look at our coefficient on the linear factor. If we're talking about a standard form quadratic, we have ax squared plus bx plus c. Okay, so think of this like our b. Okay, in order to complete the square, we're going to add on something in parentheses that will take these two terms, make them a trinomial, add something to make them a trinomial, but specifically a trinomial that's going to factor like this, what we call a perfect square trinomial. So there's a specific way to determine what number we would need to add on so that that little cluster would factor in the way we want. So what we're going to do is take our linear term, and I'm just going to write generically what we do, and then we'll look at it for this example. We're going to take our linear term, its coefficient, again, which we call b. We're going to divide that number by 2, and then we're going to take all of that and we're going to square it. We're going to add that number inside parentheses, and that's going to create something that factors in a very specific way. Now, why is that legal to do? It's legal to do because we're going to do it on the other side as well. Whatever number we choose to add on right here in order to create something that factors, we also have to add it on the other side of the equation to keep everything in balance. So if this is our value for b, okay, we're dividing it by 2. So 2 divided by 2 is going to give us a 1. If we take a 1 and square it, well, 1 squared is still 1. So inside of parentheses, I'm going to add on a 1. And I'm going to keep it in parentheses. All of this is grouped together because we're thinking of this as one unit that we're then factoring. And again, I need to add it on to the other side as well in order to keep things in balance. Now, what's the benefit of doing this? What we now have is what we call a perfect square trinomial. If we were to factor this generically, which we can do, we're looking for numbers that multiply to give positive 1, that also add to give positive 2. So those two numbers would be both positive 1 and positive 1. So as we factor this into two binomials, the binomials are the same. They're both going to be x plus 1. So we can rewrite that as x plus 1 squared. I'm going to put a star here so we know to go over and look at that. Okay, so this factors as x plus 1 squared, and then we have our plus y squared, and then that's equal to 1. And now we essentially have this particular form. Notice we have a binomial for x. We don't have it for y because there was only one term involving y, which just means we leave the y as is. But this is going to be the preferred form for our equation once we do a conversion for something like this. So what is this? Well, using the patterns we've seen before, we have a circle. So these two terms are both squared, or this factor, each of these factors is squared. It's a circle. It's not centered at the origin though. This particular value that's added onto x tells us that the center of the circle has been moved. So if you remember what happens when we add on a number to x or subtract a number from x, that's going to be a horizontal shift. So it's going to shift us horizontally by not positive 1 units, by negative 1 units in the negative direction. Now y, nothing is happening to y, which means the y coordinate for the center is still 0. So in this case, we've shifted horizontally negative 1 units, and the y coordinate is still 0. So the new center is going to be negative 1, 0. And the radius is always going to be the square root of the number on the right-hand side. So this has a radius of square root of 1, which is 1. So in this case, seeing this equation is maybe not as informative as seeing this equation. However, what we're going to look at in the next video is how we can generalize these kinds of equations in terms of what they tell us about the associated graph. Graphing directly from polar coordinates rather than converting to rectangular coordinates and identifying our graph from that point of view. So just to recap what we've looked at in this video, we introduced the polar coordinate system. We've talked about how you can graph polar coordinates r and theta, how you can find multiple representations of the same location in polar coordinates, and also how you can convert polar coordinates to rectangular coordinates, in other words, x and y. We can also take a rectangular ordered pair and convert it to polar coordinates, just depending upon the goal. So those conversions are very flexible. We can do them in both ways. And then we also used our conversions in terms of equations. So every equation in x and y can be converted to r and theta. Every equation in r and theta can be converted to x and y, just depending upon the goal. In some cases, a rectangular equation is going to be simpler. In some cases, a polar equation is going to be simpler. And again, in the next video, we're going to generalize these polar equations and talk about what their graphs are going to look like in general.